All right, so we're going to move on to example 3. It says, understanding continuously compounded interest. So just as a quick recap, we did various compounded interest, like compounded monthly, quarterly, twice a year, 4 times a year, 12 times a year, whatever it was. And we used this formula when we were doing that. And this has a really simple example to kind of show you what continuously compounded means. So it says, what if you just invest $1? So, your starting amount is $1. And the example they're using here says it has 100% interest. So meaning it pays full amount. It'll double every year. So 1 year compounded once, it'll double your money. 1 year compounded 10 times will more than double your money because you're getting that interest on itself over a period of 10 times, then 10 times, and 10 times. So it's going to be more. 100 times per year, you're going to have more. 1,000 times per year, you're going to have more. What you notice, though, is it's not like a linear increase. It's increasing, but not by a huge amount. 10,000 times per year, 100,000 times per year. You notice this number starts leveling off. So it isn't an infinite increase. It doesn't increase up, indefinitely. It starts leveling off towards a number. And mathematicians found this, and they were like, oh, this is really weird. And so they gave this number a name. This is kind of one of these numbers, kind of like pi, that they just discovered that's sort of a naturally occurring number. They call this the natural base, and they use the letter E for it. You've maybe seen this in your calculator. If you're using a graphing calculator, that E is, it's second, and then it's going to be right here. You have the ln key, so it's like second, and this ln key will give you that E to the, and they always put a power on it. You'll see why here in a second. If you're using like a scientific calculator, it's again on here somewhere. You just got to look for that little E. Again, mine's another one of these. It's a second something, so I go second here. If you're using like your phone, a lot of phones, if you turn it sideways, will have that E option on there. So you can find it a bunch of different ways. So this special number is what they noticed is when you compound something a lot, 1,000, 10,000, 100,000 times, you go up to 1,000,000 and so on, it starts leveling off towards a specific number, this 2.718 number. And so they just called that a special number and said, all right, we can call this continuously compounded interest, basically saying you don't have to do the calculation to compound it 100,000 times. This is going to be applying interest over any amount of time, meaning you could set, hey, you can stop after 1 year, 7 months, 3 hours, 7 seconds. You can stop, boom, and plug those numbers in, and that's going to allow you to use this type of a calculation. A lot of your interests on things, on loans, mortgages, etc., are compounded continuously. So it's useful to understand this equation. Some are compounded quarterly, some are compounded monthly. You just want to, if you're looking at something like that, you want to read it, you know what calculation to use. So anyway, this is our formula for continuously compounded interest. It's the PERT formula. So A equals PERT, where A is the amount you're going to be getting out of it. So they say the value of the account. P is what they call the principal. Anytime you're investing money, they call the part that goes in the principal. Or if you take out a loan, the amount you're borrowing is called the principal. E is what we just talked about. And then R is whatever the rate is. So the annual rate written as a decimal. So we've been using that a lot. But this would be like 0.02 for 2%. You don't have to add the 1 to it. And then T is going to be your amount of years. Okay? All right, so they give us a problem here. Let's just work one out. It says if you continued it for 1 million, will the value increase or decrease? Well, we know it's going to increase because every one of these got slightly larger. This one, very tiny amount. And so that is going to happen as you go another bit. Basically, that's because that's the pattern that all of them follow. So, but again, it's going to be a very tiny amount. It is not going to be much different than the 100,000. Okay. So that is the pattern, and they always increase. If you did 1 billion, if you did 1 trillion, it is going to be a little more, but it is going to keep approaching this decimal. And so this has been found. I don't know how many decimal places they go out on this, but you can, if you look it up, it's available. So anyway, let's do a calculation with this. So this thing called continuously compounded interest says Regina invests $12,600 in an account that earns 3.2 annual interest compounded continuously. So that means over the year it gets 3.2% interest, but it's compounded all the time so that no matter when you pull your money out, you're getting that interest. Okay, so that's why continuously compounded is used in a lot of cases. You don't have to wait the full year to get the 3.2%. You can pull it out after half a year and get a portion of it. Okay. So it says, what's the value after 12 years? So it really just boils down to is knowing how to put it in the equation correctly. So the principal, that's her starting amount. She had $12,600. E is always E. It's going to be just E in the calculator. The rate, 3.2%. We convert that to a decimal to be 0.032. And the 12 years be multiplied by 12. So this is what we want to calculate. And again, if you're using a calculator, which you're going to have to use because you're probably not computing E by hand. Second and natural log key is where mine is. So it's right here. And then make sure you get this in the whole numerator. So I'm just going to type it like this, 0.032 times 12. And that'll be fine. That'll do exactly what I want. I want these things to be multiplied, E raised to that power, and then multiplied by my principal. So, and there we go. We get a number. And you got to look if these make sense. So this is 12 years of investment, a pretty good 3% interest rate, $18,000. This answer makes sense. This looks like about what it should be in terms of how much money you should have at that rate. So there we go. So that would be her amount compounded continuously. Okay. All right. So there's another example here. The real key is just making sure you know how to enter this in a calculator. So I'll run through it again with this one. If you want to pause it and try it on your own, you can go ahead. But if you want to follow along, you can do that too. So this one, 125,000 is our principal. E to the RT. So the rate is 0.0475 T. And then we can put in various T values. Now, because there are two of these, I'm going to go ahead and just put this in my Y equals, and then I can just go look up my values. So 12500 E, and then in those parentheses, I'll put my 0.0475 X. And so now I'm going to jump to the table, and I'm going to go look up 15 years and go look up 30 years and go from there. So 15 years is 254,885. And I don't know if you noticed or not, but if you highlight here, you can look down, you can actually get the decimals. Like if you want to include the cents, you can. And 32 cents. And then if we take it on down to 30, we can get that one as well. So same thing here. 519,732 and 23 cents. Alrighty. Okay. And so this is actually a kind of interesting thing. And we'll talk about this a little bit going forward. But if you're investing $125,000 at this rate, after 15 years, it's more than doubled. And after 30 years, it's basically quadrupled. Just to point this out to you, think of this in reverse, which is a little different. But if you borrow this amount of money, which is what you would do to buy a house, you take out $125,000 or probably more to purchase a house. This is what interest rates are sometimes around. Right now, they're around they're at like high 2s or low 3s%. But this is a reasonable interest rate. What this means is when you pay a house off, now this would be if you waited 15 full years to pay it off. This is the amount you would actually owe. Now, generally, the way houses work is you pay a mortgage and you pay a portion of it off at a time. But yeah, when you borrow $125,000 to purchase a house, you're going to pay way more than that over the life of the loan. That is actually always presented. There's calculators that you can use for like online and stuff like that. But it's really important to know that, yeah, this is cool when we're talking investing, and you should definitely invest money when you get the chance to. But you also understand this applies in reverse when you're borrowing money. So when you are borrowing money at a rate, you over the life of the loan end up paying lots of money. Now, yes, it would be a little lower because let's say you borrowed this, but you're paying back, I don't know, $500 every month. That's going to knock this principal down. And so over the course of the loan, you're probably not going to pay back this much, but you're probably still going to be paying, $200,000 or so. And like I said, when you get to that point where you're doing those types of loans, there are calculators online where you can input the information of what you're paying per month and all that kind of stuff, where you can actually see that information. So yeah, definitely a useful adult type thing that you will at some point have a loan, have a mortgage where you're borrowing money and you're paying it back. And it's important to know how much you actually pay back over time. And why would it be more important to pay it back in 15 years versus 30 years? Actually, what's funny is these are the exact numbers that most mortgages are set up at. You can choose to pay your house off in 30 or 15 years. And these are kind of some of the differences you run into. And if you wait this long, you pay a lot more over time because it's building interest as it's sitting there with you owing money. So very important stuff to think about as you get older. You start having to buy, large cost items, and you understand how that works. All right, so don't be that person that posts stuff on social media saying you never learned this in high school, because you do. It's a real thing. All right, you got some problems today to try out. Mainly working with this PERT formula for continuously compounded interest.